Hello and welcome to another edition of my lecture video series. Today's lecture supplement, I wanted to work through an example of the conservation of momentum and conservation of energy in a collision. So we're taking an elastic collision, and this is going to be in one dimension to make things a little easier. Unfortunately, even limiting to one dimension, it's going to get a little bit messy. We have to use two conservation laws, conservation of energy and conservation of momentum. And the basic problem that I've come up with as an example is we have a pair of carts that are on a one-dimensional track, and they're moving initially in the same direction, and they have magnetic bumpers in the sides that are facing each other. So there's maybe a magnet here and a magnet here that are north to north and south to south, so that they repel each other. And so what that would do is they are initially moving like this, and then one of them catches the other, and instead of colliding and making a sound and losing energy, they collide gently so that this one moves off without any loss of energy from the collision. And these are some fairly common lab demo equipment. I know, for example, that Pasco puts out these things. So let's see a quick example with a couple of carts like that. So I take my second cart to have a mass of 2 kilograms and an initial speed of 2.1 meters per second. And I take the first one to have a mass of 1.5 kilograms and an initial speed of 1.05 meters per second, and they're initially moving in the same direction. So we need to conserve energy, and we need to conserve momentum. So energy conservation gives us the following. E initial has to be equal to E final. And specifically, we're talking about kinetic energy here. Kinetic energy in general is going to be 1/2 mv squared of cart 1 plus 1/2 mv squared of cart 2. So we can actually calculate what the energy needs to be for the initial and the final condition, because we have both masses and both speeds initially. So plugging those numbers in, I get 1/2 times 1.5 kilograms times 1.05 meters per second quantity squared. That plus 1/2 times 2 kilograms times 2.1 meters per second squared. And so what I end up with is that the initial kinetic energy is going to be about 5.237 joules. And that is my initial kinetic energy, and that's conserved, so that's also going to be equal to my final kinetic energy. Okay, so I can also do the same thing with momentum, because I have the initial velocity, both magnitude and direction of both, and the initial masses. So recall that momentum is going to be mass times velocity. So in this case, I get mass of number 1 times the speed of times the velocity of number 1 plus mass of number 2 times the velocity of cart number 2. So I can plug these things, the numbers in for these guys, and what I end up getting is that the initial momentum is going to be something like, let's see, 5.775 kilogram meters per second. And because the initial and final momentum are the same, this means that this is also equal to the final momentum. And incidentally, if I wanted to be really rigorous, I'd note that this is a positive number and that right is positive. So something like that. Okay, so that's sort of steps 1 and 2 of solving this. I'm basically going ahead and solving the numbers for the initial and final out the gate, because then I don't have to deal with a whole bunch of mass 1 times speed 1, mass 1 times speed 1 squared terms for the initial conditions. I can just treat it as one lump product or one lump result. So now that I have this, I'm going to sort of write a little reminder up here that I have the initial energy, or that I have the energy of the system, and that's going to be 5.237. And I have the momentum of the system, and that's going to be 5.775. Units of momentum are kilogram times meters per second. I'm going to use the alternative unit, which is newtons times seconds, just because it's more compact. And so now that I have that, my next step is that I have to, I'm ultimately looking for the final speeds of these two guys. So my next step is to use this conservation law. And basically I note that M1 times V1 final plus M2 V2 final has to be equal to the final momentum, and that final momentum is this thing that I found before. So I'm just going to put in a P for momentum there. And then I have conservation of energy. So this is momentum. Conservation of energy says 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared has to be equal to the final kinetic energy, which is the kinetic energy that we found in step 1. Okay, so this makes a system of equations. We could call this equation 1 and equation 2, if you will. And so if I want to solve for the final speeds, what I need to do is solve the system of equations. So what I'm going to do is I'm going to go ahead and solve the first equation for the final speed of cart number 1. So V1 final is going to be momentum minus the momentum of number 2, so M2 V2 final divided by M1. So now that I have that, now that I have this, I need to substitute it into the equation number 2 wherever I see a V1F. So that's right there. So that means that I now have 1/2 M1 times P minus M2 V2F over M1 squared plus 1/2 M2 V2F squared is equal to EK. So I ultimately am wanting to solve, I guess now for the final speed of cart number 2 first, and then from that I can get the final speed of cart number 1. So basically I have to square this mess, and what I'm going to go ahead and do before doing that is I'm going to get rid of this 1/2 and just move it over here. And then I'm going to subtract a 2 EK from both sides so that it looks a little more like a quadratic. this thing right here I should multiply out is going to look like 1 over m1 times p squared minus 2 p m2 v2f over m1 plus m2 squared over m1 v2f squared. So that's this term, and then I have plus m2 v2f squared minus 2ek. So it's a little bit of a mess at this point, and the thing to do from here is to sort of consolidate like terms. I basically want to end up having stuff times v2f squared plus stuff times v2f plus stuff that's not multiplied by v2f. Of course, this is all equal to 0. And so it ends up looking like a quadratic formula. And so I need to rearrange things a little bit to make that happen. So what I'm going to do is I notice that these terms right here and right here are the v2f terms, and these two terms right here, and this one term right here is the v2f term, and then this thing and this thing need to go together as the term that does not have any vf in it. So I'm going to rearrange this thing just a little bit by writing, first of all of my v2f squared terms. So v2f squared is going to be times m2 squared over m1 plus m2. Okay, so that, now I need to get my v2f terms together, and that is just this term right here. So I have 2p m2 over m1 times v2f. So that's my second term, and then I need to get all the other terms together. So 1 over m1, that's p squared over m1 minus 2ek. So that's equal to 0. And the reason why I spend so much time getting it into that form is basically because what this lets me do is I have some equation that has the form a times x squared minus b times x, or plus b times x, plus c is equal to 0. So that's just your regular quadratic formula, where this term right here is a, this term right here is b, and this term right here is c. So at this point, I would recommend just plugging numbers in for those, just so that we don't have to carry all this stuff into the quadratic. I'm going to go ahead and erase this top line here again.